All right, welcome back. This is again continuing ECEG 431's Project 3, looking at memory. We just talked about how it's really important to only read signals from the chips when they're stable. And I'm saying that cool and good here. I thought I'd change that, but it's staying there now. So kind of quote back to computer, what we want to do is in the system, we want to orchestrate everything so that only look when it's stable. And we need a way to agree and synchronize our watches. We only look at those good points. That's where I had this idea about a clock. It's almost like this external source is kind of orchestrating everything, like a conductor saying, now, wait, now, wait. And so if we all can kind of follow along to that clock's roll, then that's going to keep us all synchronized and all on the same page, and that's awesome. What's really super cool about this is, as we saw how the chips are kind of bouncing around waiting, it takes some amount of time for everything to get stable. If we just wait and the clock is running slow enough so that whatever chip it's taking to bounce around, do all the transitions, taking some time, if we just wait, when the clock rises up and says, look now, then it doesn't matter how slow these things are. They can take as much time as they need. Other chips which make transition faster, they can do their processing, be done. We all just wait for the clock, and that synchronizes us. We can go to the next step. And that's really, really nice. We're all now running at the same page. We can kind of all work together and be happy. And that's the big, big, big idea I want you to take away. We care about the clock, and that's going to synchronize everything that we do. So if we look at this chip behavior over time, we're going to look at a NOT gate. We have physical time flowing on the top, just kind of time is never ending, always marching on. And so what we want to do is break this continuous time up into discrete moments. And that's kind of the idea of what's going on. If I can get my thing back. Right around there, when that clock is rising. That's kind of the discrete moment that we want to just look at. So we're going to break time into these blocks or chunks. So we have 1, 2, 3, 4, and 5. So we have our input signal. Input 1, right now it's showing this input 1. Between time 1 and 2, it transitions to a low value and stays low up until right before time 4. And so in actuality, it may be that, for instance, here we might have a nice sharp transition. If we zoom in, it might look at, well, it's actually kind of taking some time. Maybe even slower, I don't know, but there's lots of options how it could take, and we don't know exactly what it's going to be. If we'd ever try to read the value here at that point in time, it's somewhat undetermined exactly. But if we wait till right here in the middle, kind of where this clock is rising and going up, which we draw as the rising edge, at that rising edge from the clock, if we wait and read it there, we are stable. And likewise, everything else, it's nice and stable. And so that's what the clock is doing. It's helping us just know when to read that. So the idea is that if we look at these discrete points in time, then everything should be stable for us. And we don't have to worry about these kind of weird edge cases where things might be jumping around. So that is an important design decision. And then that would tell us that the longest circuit we have tells how fast we can run the clock. And that comes to play with like your processor speed on your computer and how fast the clock speed is. Typically we don't talk about that as much anymore, but 15 to 20 years ago, that was a really important design metric. People try to overclock and clock as fast as they can because they could process more data. So on our big map for the CPU, if we were working on making the central processing unit, we need memory to make our CPU function correctly. So we have this big ALU, which we've already built. That is on the CPU. That's the main chunk of it. We just need some other routing signals. We also have a few registers, which are just on-chip memory blocks. And we have a much larger set of memory for the system memory. That's going to have all the main memory segments that we use. Many registers in that, very few on the processor. Typically on a processor like in your computer, there are several layers of registers, and depending on how close they are to the CPU, kind of both physically close and also as an abstraction, is how fast they are. So it's very quick to write to and from registers on the CPU itself. It takes a lot more time to write to memory, especially if that's off the CPU and to get on the data bus. And we're going to talk about all that. So this is the way our CPU looks. We have inputs into the CPU that has memory, the ALU, that kind of work in conjunction with each other, and then we have outputs, and that defines what our computers will be building in the next project. So we're going to have a memory hierarchy. And to store information, we need to be able to load a bit into somewhere. And I'm saying that vaguely because it doesn't really matter where it goes, just as long as we can recall it. So if we put that bit somewhere, time passes and we say, please return that bit and tell me what it was, and we can recall that bit. As long as it's not changed, it's fine. The specific where that bit is not important to us because we just want to be able to store something. Then later we'd like to be able to load a new bit and overwrite what we have currently stored. So if we build in these basics, we want to store a set of 16 bits together, because that's going to be a 16-bit value. We want to store that bundle of 16 bits together somewhere, wherever that is. And we'd like to store other sets of 16 bits in this kind of magic bag that we have. And sometime later we'd like to recall them. If you're a fan of role-playing games, this is like a bag of holding. We just want to take 16 bits, stuff them into our bag, and then at some point later recall, oh, I want whatever that value is, reach in, take it out, and it has not changed at all. So that's what we're going for. Where it exactly is stored, it's okay. And this leads to you, because you're going to build a memory hierarchy, and it's not terribly important exactly how you do it, as long as I load a certain address and say, I want this location's memory, please give it to me, and it will return something. So the basic building block, and of all this is going to be built up from, is something called the D latch. And if you are in a logic course, you'd probably spend a lot of time kind of building this up and figuring out what's going on. But this is called a D latch. And this is able to latch onto data and hold onto it. When E, this is a little bit of a blurry slide. We have E, this bit here. When E is low, the circuit is going to maintain the last output value. So if you look at an output, this Q signal, if E is low, then we just keep that value. Whatever is going on over here on our data input, it was not going to affect D. The reason is that it does take time for this signal to kind of update and travel through and propagate through, and then it's going to reach a stable position. And while this E is held low, this is in a self-supporting state. When E is then high, then the data on the input pins here is going to pass through, and then when E drops back down low, it'll enter into the self-supporting state. The book talks about this a little bit more, and if not, I have other notes I'm happy to share with you about that. But this is a building block, a D latch. And what this is, I guess the key thing here is a D latch is transparent. And what that means is that when the enable bit is raised high, whatever value is on D is going to be passed through and output on the Q state. When E is low, it is then latched and storing that. Now I talked about a clock earlier, and the issue is we can kind of do this with the clock, but if we just raise E high, then all those fuzzy bouncy signals are going to pass through, and we don't want that. We want to discretize time into that little instant around the clock. So instead, if we place two latches in series, this is a D latch, and this is a D latch. If we have these two latches in series together, this is going to be the primary and the secondary, and this is going to form what we call a D flip-flop. Essentially what happens is the first latch is going to pass along whatever values in D. These will pass through transparently when E is high, and the second one will pass along whatever its input when D is now low, because of this not carry here. The result is, on a clock edge, the circuit is going to update its value. So as we have edges of clocks, we have rising edges and falling edge. I believe, I need to look closely again, but let's just say it's a rising edge of a clock. This might be a falling edge, but let's just say if it's the clock edge happens, we transition from low to high on the clock input. The value here on D will then be updated on Q, and it will stay that way until the next rising edge of a clock. And that's the big abstraction that we want to care about. Time only matters on a clock edge. At other points, it's not really going to do anything. We don't have to think about it. Okay, I'm going to stop there for now, and I'll come back in just a second.